So good morning. So today I present the modification of the standard ICP algorithm using the fast point detection method and local optical flow for the 3G registration problem. So I first describe the problem, then I present the novelty of this work and compare it to the standard ICP method and then the conclusion part. So first, in this application of the registration and actually in that case the augmented reality problem, we are using the RGBD images, mostly from the Kinect camera. That is on the first image. Then we have a 3D model that we want to render in the specific location on the scene. And so we need to calculate where is the camera and where is the other part of the environment. And on the last image, we can just show that we can render the in this case, this dinosaur image on the proper position. For this work, we actually using the standard projection from 2D information from the deep map and the color from the original RGB image into the 3D point cloud. To register the point clouds, we applied the standard ICP method, but we found that this method is quite complex and is not really applicable for the real-time applications. And the other problem is that there exists like holes on this deep information. That is a problem with the rendering of the scene, and it gives the problems to calculate the occlusion of the parts of the scene when we render AR image. There are two main strategies. The one is just to select some points from the 3D cloud point and use it to calculate the position of the camera. For instance, the PTAM is a main method. Or there's a dense approach, so where all the pixels are used. But both of these methods have some problems. And in our work, we are looking which points to select to have the best results. So there are many different approaches, like a random or pre-selection, but probably right now in literature and experiments, we found that the best way is just using the points that are near the areas where the gradient of the pixels are significantly different. So for instance, that are like characteristic points or corners or curves, edges, but not like flat surfaces. And here is the structure of the algorithm that we built. So first we select the points, then we apply the local optical flow, project that in the 3D space with the context of the movement of the selected points. And then we use only the part of the ICP method to calculate the camera position and the transition, so that is a rotation and translation matrix. The standard ICP method consists of the two main steps that are run in each step of the loop. So first is just to correspondence estimation. So we need to find the same point that on the two different point clouds. And then we do the transformation optimization. So we're looking for this matrix. So our idea is just to remove that step, the first step, from every step of the loop, and make it faster. So we apply some assumption in this case. So to compare the ICP method with the proposed method is that on the standard ICP method there is like a no context between the points. There are a match in each step of the iteration. There are some modification that using the description or shape. In our method, we are using the context that is the movement of the 2D point on the RGBD image, and then we project that into the 3D space. The next difference is that the computation complexity is quite big here because we need to do the match between the points in every step. Here, because this match is the point matching step is fixed, we don't need to do that. That is give us a very good like a saving of the time for in execution. But the drawback of this approach is that the ICP method is application agnostic, so it can be used in many different places. Our solution depends on like a consecutive images, so we need to calculate the movement of the selected points. We also modified the way how we select the points. The fast method is one of the common used, but we also apply the scale pyramid technique. So this one is actually quite good because the fast is sensitive to scale. And when we build the scale pyramid, we can just select the points that are not visible in one scale, but can be visible in many different scales. So we also need to group that points. And then we're just using the local optical flow to track the movement of that pixels. Here's a graph that describes how the AR image is built. So first we just need to track the camera movement. We need to calculate the transition of the camera, and we also need to accumulate the points from the previous frames to have like a reference to the next step. And the rendering is a standard operation here. So we decide to perform a comparison on the efficiency of the method. So it's like the time and the accuracy. And we show that this can be used for the two applications, like a scene reconstruction and the AR system. Here we apply the standard benchmark from Technical University of Monachium. And just to compare the proposed method with the ICP, the proposed method is a bit faster, and the mean error is smaller here. So here's the slide that presents the RGB image and the depth component. Here we have the projection of the points, and here is like a whole setup, so like camera position and the added object. Here are some slides from the video sequence of the AR system. So when we move the camera position, we calculate the position of the augmented object, and we just showing the augmented object on the screen. And just to conclude the presentation, so we apply two modifications here. The first one is using the space pyramid to build the set of the points that are then used to project into 3D space. We show that this proposed method is 12% faster in accuracy and 37% better, faster compared to standard ICP implementation. So the novelty of this method is to use the optical flow that can track the point movement on the 2D, not the 3D as a standard ICP. And we present that this one can be used to AR application, or it can be used, the accumulated point cloud structure can be used for the 3D reconstruction. Thank you. Any questions?
Thank you very much for the presentation. Do you have any question? Not now, so I will start. I wanted to ask about testing and validation. You had on your slides information that the method was tested on a selected data set, and then mean error and time was measured. Do you plan to do any further testing extended to validate the method on more possible data sets and source data?
So that one that I use here is like a benchmark. So it's one of the most common probably for this kind of the applications, especially for the 3G registration. And of course, it's possible to just extend it. Just need to find the proper data set that can be applied.
Okay, thank you. And I see also that we have a question on the chat, but I also unmuted the author of the question. So if you wanted to ask it, then I won't read it.
Yeah, I just wrote it in case there are some problems with the internet, because there are a lot. So my question is, have you compared the performance of your method with that of the Google's AR core library, which does, well, very similar things, actually?
No, actually, this one was just run on the PC. So I just need to make the comparison. I just need to have the data from the AR core. I don't know if this library can give me such, like a raw data that I can use for comparison.
Well, you can extract the data in several ways. Either you can plug into the debug version, or you could use some of the built-in telemetry. But you can also measure performance using your own timing metrics. Yeah. So yeah. I was just asking if you attempted it, because it would be something interesting to see, maybe for further work.
Definitely, it'd be quite good to just compare to the standard real world application. Yeah, that's a good point.
Okay, thank you.
Okay, I don't see any more questions, so thank you for the very interesting presentation.